Okay, guys, I'm back with another video, and this is the Edexcel level 3 GCE test or A-level paper 2 advanced physics 2 from June 2025. I believe this is the most recent one. This is a very special video because I recently uploaded the solutions for paper 1, which is advanced physics 1, and someone emailed me and thanked me for that video and requested whether I can continue with advanced physics 2 and with paper 2 and paper 3 and so on. So here I am with paper 2. And by the way, if you search my videos, there is another past paper walkthrough for paper 2 from 2024, I believe it was, and you can find it in my videos. So anyway, let's dive into this paper. Okay, so so the first 10 questions are multiple choice, like all tests of this sort. And as I say in all my videos, please try to spend about a minute per question. And later, for the questions that are, say, 10 marks, the rule of thumb is to spend 10 minutes on them. Okay, it's not a hardcore rule, but it's good to keep track of time. All right, question 1. Which of the following gives the SI base units of stress? Okay, this is actually correct, but the Newton is not a base unit. Okay, it's a derived unit, so it's a trick. So stress is defined as force per area, right? And to work with units, I use those brackets. Okay, so the units for for force is newtons, for area it's square meters, and then we have to recall that 1 Newton is 1 kilogram times meters per second squared, and then we have the meters squared in the denominator, which reduces to kilograms, meters to the minus 1, and then seconds to the minus 2, which is option B. And whenever you have trouble analyzing a derived unit into its base units, so here in this example we have the Newton. Notice, okay, that this is 1 Newton. What's the definition of a force? Force is mass times acceleration. So mass is in kilograms, acceleration is in meters per second squared, and you can immediately find the definition for a Newton. Okay, so if we put the square brackets again, we see that newtons are equal to kilograms meters per second squared. Okay, I hope this makes sense. Let's move on. Which of the following provides for the particle nature of electromagnetic radiation? And diffraction is not the case, interference is not the case, the photoelectric effect is the case, okay? And polarization is totally irrelevant. So the idea is that the photoelectric effect proved that a photon of energy h times its frequency provides energy to extract electrons from metals. Okay, so it provides energy to overcome the work function, and then once the electrons are out, they can have a kinetic energy 1/2 mv squared, m times v max squared. Okay, so moving on, question 3. Light enters a semicircular glass block as shown. The ray of light reaches the straight edge of the block at an angle of incidence theta. The critical angle for glass is theta. Which of the following statements for light incident at the straight edge of the block is correct? So let's read it again. So the critical angle is C. Okay, so option A, when theta is greater than the critical angle, then no light is reflected. That's not the case. When theta is greater than C, then no light is transmitted. Okay, that's total internal reflection. So B is the correct answer. C states that when theta is less than the critical angle, then no light is reflected. That's wrong. Actually, light is reflected in that case. And then when theta is less than C, then no light is transmitted. No, totally wrong. Okay, 4. Scientists believe that our universe is currently expanding. One possible fate is for the universe to reach a maximum size and then start to contract. Which of the following descriptions of a universe with this fate is correct? Okay, so the great contraction would happen when we have a closed universe, pretty much. Okay, I mean, by definition. So the option A is the correct one. Okay, moving on. X and Y are identical stars. When viewed from Earth, the intensity of star X is 4 times the intensity of star Y. Which of the following explanations is possible? So the intensity of X is 4 times the intensity of Y. Okay, and the stars are identical, so the intensity is defined as the luminosity over 4 pi x squared, where x is the distance from the star. And this is 4 times the luminosity of the other star over 4 pi y squared. So the luminosities are the same, so they can cancel. 4 pi, the factor of 4 pi cancels. And we immediately see that y squared is 4x squared. Therefore, x is 2, sorry, y, the distance of star y, is 2 times the distance of star x, which is literally option C. Y is twice as far away as x, okay? And we worked out the proof. Okay, question 6. A trolley is attached to 2 springs and set into horizontal oscillation as shown. Okay, stand spring, okay. The kinetic energy of the trolley is EK and the potential energy of the trolley is EP. Which row of the table is correct? When the trolley is at its equilibrium position, then the kinetic energy is maximum, right? Because it momentarily stops when it reaches the maximum displacement, and then it starts moving towards the equilibrium position, which it passes with maximum speed. So only options A and B could be correct. And then when the trolley is at maximum displacement, then the potential energy is maximum because the spring is fully stretched, right? So B is the correct answer. Okay. 7. A small ball bearing falls slowly through a liquid at terminal velocity. The temperature of the liquid is increased. Which of the table shows the change in viscosity of the liquid and the change in terminal velocity of the ball bearing? So the viscosity decreases, right? Because for liquids, if the temperature increases, the viscosity decreases. And if the viscosity decreases, the terminal velocity increases, right? So the only correct option is C. Okay, it is a little bit of a tricky question, so let's read it. Some rocks contain polonium. The polonium is radioactive and decays to a stable isotope of lead. Polonium is a very famous radioactive element because it's used as poison sometimes. Okay, I mean in spy operations and such. I'm not gonna say more because this is not a channel about politics, but I mean this is something they do. Okay, which of the following graphs shows how the number n of lead atoms produced by the decay of polonium varies with time? Okay, so you might be quick to say that, oh, A is the correct answer, which is not, okay, because they don't ask anything about polonium. They ask how the concentration of lead atoms, which are produced from the decay of polonium, varies with time. So what they say is that polonium turns into lead, right? So initially we start with 0 atoms of lead. So the only possible answers are B and C. Now, when polonium decays, it follows the formula or the decay law, n is equal to n naught e to the minus t over tau, right? Now for lead though, okay, it's like the charging and discharging of a capacitor. So this is sort of like the discharging curve, but for lead, the actual formula is n is equal to n naught minus n naught e to the minus t over tau. Okay, so this is actually option B. So this is like the charging phase of a capacitor. In the charging phase, Q is Q naught minus Q naught e to the minus t over tau, right? Yes, the correct answer is B. Okay, so you can think of like the analog of charging and discharging of a capacitor. Okay, because here we are studying how the concentration of lead atoms is increasing. All right, option 9, light from a lamp passes through two polarizing filters, P1 and P2 as shown. The light intensity is recorded by a detector. The filters initially have their planes of polarization parallel. Okay, both filters are rotated in the same direction. Which row of the table gives the changes that result in the minimum intensity of light at the detector? So to have a minimum intensity, you need to have the two polarizers perpendicular to each other. Okay, so polarizer 2 must be rotated in this direction so that it becomes perpendicular to P1. Okay, in other words, the trick in this kind of question, in these kinds of questions, is that whatever the rotation of P1 is, then the rotation of P2 has to be whatever P1 is plus or minus pi over 2. Okay. In other words, for example, in the first option A, delta phi is pi over 4, right? So that's wrong. Okay. In the second option, delta phi is 3 pi over 4. So that doesn't work either. C works though because delta phi is pi minus pi 2, which is pi over 2, right? So the two polarizers are perpendicular to each other, okay? And then similarly, D delta phi is simply pi. That doesn't work, okay? So I hope this makes sense. Again, if something doesn't make sense, please ask a question in the comments and I always reply. So. All right, and finally, for the multiple choice section, the diagram shows how displacement varies with distance for two waves x and y at a particular instant. The waves are traveling to the right. Okay, so they move this way. Which of the following statements describes the phase relationship between the two waves? So you can pretty much see it. I mean, from the graph that this is a maximum when this is a minimum. So it's pi over 2 ahead. So x is pi over 2 ahead of y, or 90 degrees, or option A. So what do you mean by that? I mean, if you extend it backwards in time, okay, so you see that x is at this position pi over 2 earlier than y, pretty much, okay? All right, moving on. Question 11. A spectral line with wavelength 655.82 nanometers is detected on Earth from the Triangulum galaxy. The wavelength of this spectral line, measured using a laboratory source is 656.28 nanometers. Calculate the velocity of the Triangulum galaxy relative to the Earth. Okay, so first of all, observe that the lambda from the triangulum galaxy is less than lambda as measured in the lab. Therefore, we have a blue shift. So blue shift, so the galaxy, I mean the triangulum galaxy, moves towards Earth. Okay? Okay, now let's find delta lambda, the change in the wavelength can be calculated by subtracting lambda lab from lambda triangulum. So we find 655.82 minus 656.28 nanometers, or minus 0.4 nanometers. Okay, minus represents the fact that it's moving towards us. Okay, so the z factor, the Doppler factor, is given by delta lambda over lambda lab. Okay, it's always lambda lab in the denominator, by the way. Okay, so minus 0.4 over 656.28 yields minus 6.09 times 10 to the negative 4. So the Doppler factor z is v over c, and this is equal to minus 6.09 times 10 to the negative 4. So v is minus 182,848.8 meters per second, and this thing moves towards us. Okay, 12, this was a very funny question. The image from the cover of a music album is represented below, and I think the album they are referring to is, let me find it. Sorry for this detour. So it's Led Zeppelin. Is it? Wait, is it The Dark Side of the Moon? I think. Let's see. Yes, Pink Floyd. Sorry. So this is the image they are referring to. Okay, so this is it. Okay, this was kind of funny. So, oops. All right. So white light enters the prism at an angle of incidence of 45 degrees. The light disperses and splits into a spectrum of colors as it enters the prism. In this image, the angle of refraction for violet light at the first boundary is 22 degrees. The angle between the red light and the violet light is 11 degrees. Evaluate whether the angle between the red light and the violet light is accurate. So they are referring to this angle. This is not the kind of question you expect at the A levels. So, but it's funny, it's cool, it's a cool question. So, all right, so let's start with the interface between the incident light here at 45 degrees and the violet light. So this angle here. Let's find that angle. Okay. So let's start with that. So n air times sine of 45. I'm using Snell's law. Is let's call it nv for violet light times sine of 22 degrees. Wait, what did I say? I said that we are looking to find that angle. We actually know that angle is 22 degrees. Excuse me. Okay, mistakes happen. But we don't know the index of refraction of the prism. Okay, so using this formula, we can find the index of refraction for violet light, and then we will see how to find the index of refraction for red light. Okay, so let's do this. So n violet is pretty much, this is 1, by the way, for air. Sine of 45 over sine of 22 degrees. which is 1.89, which is blue. Okay, so now in blue, we are also given this information that the speed of violet light in prism over the speed of red light in prism is 0.99. So let's use the definition of index of refraction. So not blue. I'm recording this early in the morning, so apparently I need more coffee. So this is for violet, okay? So N violet is C over the speed of light for violet light in the prism. So violet is C over N violet, which is 0.53 C. Okay, let's use a clean page. Now, V for violet over V for red is 0.99, right? So V red is 0.53 times the speed of light over 0.99 or 0.534 C. Okay, so it's really close pretty much. Therefore, the index of refraction for red light is C over V red or 1 over 0.534, which is 1.87. Okay, now let's use the N red and use Snell's law again. Now with this angle 45, and then we want to find the kind of angle, we want to calculate this angle pretty much, okay, for the red light. It is stated that it's actually 33 degrees. If we add this and that, we find 33 degrees. And this is what they claim the angle of the red light refraction to be. So let's see, is this true? So NR times sine of 45 degrees. By the way, this is supposed to be a subscript. So NR is equal to N red times sine theta. Okay? So sine theta, again, this is 1. Okay? Sine theta is 0.378. So theta is 22.22 degrees, which is much less than 33 degrees. Okay, so the statement, so the album cover is wrong, but cool. Okay, and so is the album itself and Pink Floyd. Okay, so let's move on. Okay, question 13. A teacher demonstrated the photoelectric effect by illuminating a zinc plate with electromagnetic radiation. When ultraviolet radiation of wavelength 320 nanometers was incident upon the zinc plate, electrons were emitted from the zinc surface. When visible light of wavelength 420 nanometers was incident upon the plate, no effect was observed. Explain these observations. Your answer should include calculations. And we're given the work function of zinc, okay, which is cool. So basically, all we have to do is to use to find the energy of these photons, okay? So the energy is h times, Planck's constant times the frequency, and then the frequency for electromagnetic radiation is always equal to the speed of light divided by the wavelength, okay? So we'll calculate the energy for this radiation, I guess, and compare with the work function and see if there is enough energy to extract electrons from zinc. So let's start with the UV, okay? And if we just plug in numbers, 6.63 times 10 to the negative 34. And again, I'm going to put all the units to the right. So the units for H are joules times seconds, okay? C is the speed of light, 3 times 10 to the 8, and then meters per second. And then in the denominator, we have the UV wavelength, which is 320 nanometers. So 1 nanometer is 10 to the negative 9 meters. All right, so seconds cancel, meters cancel, and we find units of energy as expected. And the answer is 6.22 times 10 to the negative 19 joules. Now recall that 1 electron volt is 1.6 times 10 to the negative 19 joules. So if we divide joules by 1.6 times 10 to the negative 19, we will find the energy in electron volts. And this energy is equal to 3.88 electron volts, which is larger than 3.74 electron volts, which is the work function. Okay, so electrons are emitted. Okay, and let's do the same for the second radiation. Let me use a clean page. So the energy of the, let's call it visible light, because it's 420 nanometers, that's blue-ish, okay? So 6.63 times 10 to the negative 34 times 3 times 10 to the 8 over 420 times 10 to the negative 19, and this is joules. We proved that before. And this yields 4.74 times 10 to the negative 19 joules, which is equal to 2.96 electron volts, which is less than 3.74 electron volts. Thus, no electrons are emitted, which is the essence of the photoelectric effect. If you don't provide photons with appropriate energy such that their energy exceeds the work function of the metal, whatever the metal is, okay, you will never see any electrons emitted, okay, which is what Einstein postulated, and then it was discovered, and he got the Nobel Prize from it, and so on. All right. Question 14 is a long writing problem, okay, because it has the asterisk, and it gets and it it awards 6 marks. So this means that, okay, the question should take you about 6 minutes to draft, maybe 7, I don't know, so somewhere there, and you have to provide at least 6 statements that prove or disprove whatever the statement they give you, or whatever the question they ask you asks. Okay, so air molecules are trapped in a container by a piston as shown. The position of the piston is adjusted so that the volume available to the air molecules is reduced. The temperature, so the volume is reduced, is the first key. Okay, and then the temperature stays the same, is the second key. It's constant. Okay, explain how the pressure exerted by the air changes. You should refer to the motion of the air molecules. Okay, so we can write many things here actually. So the pressure increases, okay, when the volume is reduced. When the volume is reduced, okay, and recall, let's write it in parentheses, recall that P times V is NKT. Therefore, P is NKT over the volume. Okay, so if the volume decreases, the pressure increases. Okay, so that's the complete answer. In this case, the number of molecules N is the same. I mean, nothing escapes the piston, right? The temperature is kept the same. I mean, they tell us that. So the volume decreases, therefore pressure increases. Okay, second observation, the temperature remains constant. Okay, remains constant. Okay, so the average speed of the air molecules remains the same. Okay, and this goes back to the formula 1/2 m, and then the average squared speed is equal to 3/2 kT. Okay, so if the temperature is the same, the speed remains the same. Okay, next point. I'm gonna use a clean page. With a smaller volume, okay, with a smaller volume, with a smaller volume, the molecules travel a shorter distance. Travel a shorter distance. Okay, before hitting the piston or the walls. Okay, this means the fact that they travel a shorter distance. So this means the molecules collide with the piston or wall, collide with the piston or the wall more frequently. And you can see this from simple Suvat equations. S is V times T, right? So with this, the average distance reduced and the speed remaining the same, the time reduces, between collisions. Okay. The change in momentum, the change in momentum, the change in momentum in each collision, is about the same. Is about the same because delta P is m times delta V, and the V is the same. Okay, but collisions are more frequent. Okay, so the rate of change of momentum, so the rate of change in momentum increases. Okay, increases, which means a greater force, which a greater force, okay, on the walls and pistons is exerted. Okay, and finally, since pressure is force per area, when the force increases, the pressure also increases. Okay, and this is more than enough of an answer. I don't know. I made it too detailed, so you don't have to, but I put all the points I could think of. Okay, so let's move on to question 15. A pulsar is a rotating neutron star. The pulsar emits electromagnetic radiation as it rotates. Scientists have recently detected the highest ever energy gamma ray photons received from a pulsar. The energy of one of these gamma ray photons was determined to be 2 times 10 to the 13 electron volts. Calculate the wavelength of these gamma rays. Okay, again, the energy of any electromagnetic radiation is hc over lambda, right? So lambda is hc over the energy. So let's plug in numbers. 6.63 times 10 to the negative 34 times 3 times 10 to the 8 over the energy, which we will convert to joules. So 2 times 10 to the 13, but that's electron volts. So you have to convert the electron volts to joules by multiplying by 1.6 times 10 to the negative 19. and this is in meters, and this is simply 6.22 times 10 to the negative 20 meters. Okay, so for reference, you don't have to write that down in a test, but if you're curious, for reference, a nucleus is about 10 to the negative 15 meters. So this is 100,000 times smaller than the nucleus, which is a really tiny object. Okay, so this is kind of crazy. All right, the pulsar is estimated to be traveling away from the Earth with a velocity of 750 meters per second. State why this motion away from the Earth does not significantly affect the wavelength of radiation received at the Earth. Okay, so we can calculate the Doppler factor. Okay, Z is V over C, right? So 750 over 3 times 10 to the 8 yields 2.5 times 10 to the negative 6, okay? And this is a dimensionless factor because we are dividing a speed by a speed, okay? So delta lambda over lambda will be 2.5 times 10 to the negative 6. So delta lambda will be, if we use the lambda we just calculated, this one, okay? Delta lambda will be 2.5 times 10 to the negative 6 times 6.22 times 10 to the negative 20. This will be 1.56 times 10 to the negative 25 meters, okay? So this is tiny, like it's impossible to detect something like that with the technology we have today. So too tiny. So that's the answer. Okay, let me sip my coffee. Okay, question 16. The closest distance from the eye where light from an object can be brought to a focus is known as the near point distance. The near point distance for a human eye is taken to be 25 centimeters. A long-sighted eye has a near point distance greater than 25 centimeters. This may cause problems with focusing on near objects. A converging lens can be used to correct this problem. The converging lens forms an image of a near object at the actual near point distance of the long-sighted eye. State the type of image formed by the converging lens when used to correct a long-sighted eye. So it's just a virtual image, right? Virtual image, and again, virtual images are formed on the same side of the lens. I mean, if this is your lens, a virtual image is on this side and it's upright. Okay, let's move on. The near point distance for a long-sighted eye is 65 centimeters. Calculate the power in diopters. I don't know how to pronounce it. Let's call it just D. Okay, diopters, maybe dioptries, dioptries, something like that. Let me know in the comments of the converging lens required. So we're just gonna use 1 over U plus 1 over V is 1 over F. Okay, U is let me use a clean page. U is 0.25 meters. V is minus 0.65 meters. So it's virtual, therefore negative. Okay. Okay, so 1 over 0.25 minus 1 over 0.65 is 1 over F. So 1 over F is 2.46, which means that F is 0.41 meters, and then the power is 1 over F, which yields 0.41, which is equal to 2.46 D, which is about 2.5 D. Okay. And question C, a diverging lens can also be used to correct problems with eyesight. Draw a ray diagram on the axis below to show the formation of the image of a distant object by a diverging lens. F marks the position of each principal focus of the lens. Okay, let's take an object here, say. Okay, so these are our object. And let's draw the rays. So Let's draw one like this. So this is how it reflects. And then there is also, we can also draw a line. Actually, I don't like this line. Let me erase this. Okay, and let me draw it like this. Okay, so, and now I'm gonna erase. Oops. I'm trying to make it tiny. Okay, cut. Okay, something like this. Okay, so this is our line. And then one more line is enough. So one that passes through the focal length and the, no, we can draw this one that goes straight like that. Okay, and the virtual image is this one. Okay. And also, if you want one more line, you can draw, let me see. If you draw this one, okay, then this reflects, okay, we can do that again, okay. Okay. And this, if you extend it backwards, it meets the other two lines where the virtual image. So virtual image. I haven't seen these things in 20 years before going through paper two, not this paper two, the previous one I uploaded in my video. So let's move on. The asteroid Bennu is in an approximately circular orbit around the Sun. Scientists consider that Bennu may collide with Earth within the next century. By the way, I have a video, I think I have two videos, where I kind of try to play around with Universe Sandbox. This is a simulation software that allows you to simulate astronomical objects. So this just gave me an idea for a future video. So maybe I will try to make Bennu collide with Earth and see what happens. We'll see. All right, in the simulation, I mean. Now, in 2060, Bennu will be 7.49 times 10 to the 8 meters from the Earth. Show that the mass of Bennu is about 7.8 times 10 to the 10 kilograms, and they give you the mean radius of 245 meters, and the average density of Bennu, which is 1,260 kilograms per cubic meter, which means that it's mostly ice, probably, because the density of water is about 1,000 kilograms per cubic meters. Then, okay, the density of air is just 1 kilogram per cubic meters. But the density of stone is 5, maybe 6 kilograms. 6,000 kilograms per cubic meter. So this tells you that it's probably mostly water. Okay. So how are we going to calculate the mass? Just simply using the plain old density is mass per volume. So mass is density times volume. This is a sphere. So the volume of a sphere is 4/3 pi r cubed. So if you plug in the numbers, we have 1,260 times 4/3 times pi times 245 cubed. And this yields 7.76 times 10 to the 10 kilograms, which you can write as 7.8 times 10 to the 10 kilograms. Okay, part 2, calculate the magnitude of the force F between Bennu and Earth in 2060, and they give you the mass of the Earth. Okay, we can use Newton's formula, G, mass of the Earth, mass of Bennu over r squared. So 6.67 times 10 to the negative 11 times 7.76 times 10 to the 10 times 5.98 times 10 to the 24. I don't know why I crammed everything in this tiny space, but okay. Over 7.49 times 10 to the 8 squared, which will give you 55.18 times 10 to the 6 newtons, which you can write as 55.2 times 10 to the 6 newtons. Part B, the orbital time of Bennu around the sun is 1.17 years. Calculate the mass of the sun, and they give you the average distance of Bennu from the sun, the mass of Bennu, and 1 year in seconds. So how are we going to work this out? Okay, so Newton's force, the gravitational force, G times mass of the sun times mass of Bennu over distance squared, provides the centripetal force needed. This force provides the centripetal force needed so Bennu will go around in a circular orbit, or this is equal to m omega squared times r. So the mass of Bennu just cancels out, and we can also, is there anything else we can simplify? No. So we can write that G times the mass of the sun over r cubed is omega is 2 pi over 2 pi over the period, right? So squared becomes 4 pi squared over t squared, and we need to solve for mass because we are interested in the mass of the sun. So the mass of the sun is 4 pi squared r cubed over g times t squared. So let me use a clean page. So the mass of the sun is 4 pi squared 1.17, right? 1.17 times 10 to the 11 cubed over 6.67 times 10 to the negative 11 times 1.17 times 3. Wait, I think I confused something. Yeah, this is 1.7, guys. I'm sorry, I made a mistake. So this is the radius. The radius is 1.7 time. Let me erase everything. I'm sorry. So 1.7 times 10 to the 11, okay, cubed, that's the distance. And then in the denominator, we have 1.17, which is the period. And then we have to multiply by 3.15 times 10 to the 7 seconds to convert the year to seconds. 10 to the 7, yes. Okay, and this yields 2.14 times 10 to the 30 kilograms, and that's the answer. All right. Moving on to question 18. Glaciers are massive bodies of slowly moving ice. Over time, a fine sediment forms on the surface of a glacier. The sediment contains radioactive isotopes. Cesium-137 is a common radioisotope found in the sediment. Complete the following nuclear equation to represent the decay of cesium. Okay, let's start with the beta particle that has a mass number of 0 and an atomic number of -1 because it's negatively charged, right? So to balance this 55, we need 56. So barium is 56, pretty much. 56 -1, 55. And then 137 is the mass number of barium. And this is because beta decay preserves the mass number. Okay. B, the concentration of cesium-137 on a Norwegian glacier was investigated. The half-life of cesium is 9.5 times 10 to the 8 seconds. The activity of cesium-137 was determined to be 2.5 times 10 to the 4 becquerels per kilogram of sediment. Calculate the number of atoms of cesium-137 in 1 kilogram of sediment. So in 1 kilogram, the activity is simply 2.5 times 10 to the 4 becquerels, because this is what is stated. Now the activity is lambda times the number of atoms. So the number of atoms is the activity over lambda, and the lambda is ln of 2 over t1 half. Okay, so let me use a clean page. So n is simply 2.5 times 10 to the 4 times 9.5 times 10 to the 8, which is the half-life, over ln of 2, which is 3.43 times 10 to the 13 atoms. Okay, I haven't checked this. Let me check the mark scheme. This is question 18, and I do have the mark scheme, but I rarely check it. Okay, that's correct. Okay, part 2, calculate the time taken for 10% of the cesium-137 atoms to have decay. So if 10% decay, right, 90% remains. I mean, it makes sense, right? This allows us to use n equals n naught e to the minus lambda t. So you can divide n by n naught, and this is equal to e to the minus lambda t. So if we take the ln, I'm coming over here. So if we take the ln of n naught, this is equal to minus lambda t. So the time is minus 1 over lambda ln of n over n naught. And you will see why I carry that n over n naught. Okay, so this is equal to minus t1 half over ln of 2, like we did earlier. Sorry, t1 half ln of 2 times ln of n over n naught. So this is equal to minus 9.5 times 10 to the 8 over ln of 2 times ln of 0.9, which is 90%, because this is simply n over n naught is 90%, okay, because this is the number of nuclei remaining, and this is what you started with. And the remaining number of nucleons is simply 0.9 n naught, right? Okay, so if we do this ln is negative because it's smaller than 1. So the answer is 1.44 times 10 to the 8 seconds. Okay. Question 19. The photograph shows a giant ice sculpture of the Elizabeth Tower Big Ben. Okay. The ice sculpture was installed in St. Pancras, I don't know, let me know in the comment, station in London in 2009. That was long ago. Wow, in 2009, I graduated from college. It feels like centuries ago. And I still haven't been to London. Shame on me. Okay, I'm not rich, guys. Fund me or find something for me to do in London, and I'm going to be there tomorrow. Okay, but yeah, for now, I haven't visited yet. So the ice sculpture can be approximated as a regular cuboid as shown below. Okay, so it's a cuboid with height 25 meters and a square base of 3.1 by 3.1 meters. Okay. A, show that the mass of the ice sculpture is about 2.2 times 10 to the 5 kilograms, and they give you the density of ice. So we will do the same as before. Mass is density times volume. So, I mean, this is the same question as the one with the asteroid, okay? So mass is 920 times the volume of a cuboid, which is 3.1 squared for the square over there, times the height to find the volume. Oops. We don't need the units there. So this yields 2.21 times 10 to the 5 kilograms, which, yes, it's about 2.2 times 10 to the 5 kilograms. Moving on, B, it is claimed that 1% of the ice would melt if the ice sculpture were in direct sunlight continuously for 12 hours. Assume that radiation of intensity I from the sun is directly incident upon the top of the sculpture as shown below. Okay, deduce whether this claim is correct. They give you the initial temperature of the ice sculpture, the intensity of the sun, the specific heat capacity of ice, and the specific latent heat of ice. Okay, this is kind of involved. So let's first calculate how much available energy we have. So let's start with this information. Okay, so in 12 hours, we will get a total energy of 1350, and this is joules per seconds, right? And then over square meters, okay? So 1350 times 3.1 squared, and this is meter squared, that's the area, this surface area pretty much, okay? So meters cancel. And then in 12 hours is 12 times 60 minutes times 60 seconds per hour. So we have seconds here, so everything cancels. So the available energy to us is 5.6 times 10 to the 8 joules. Okay. Now let's calculate the cost, like the energy needed to raise the temperature of the ice from minus 20 degrees to 0 degrees, okay? Because we have to first raise the temperature of the ice. To raise the temperature of ice from minus 20 degrees Celsius to 0 degrees Celsius, we need an energy of the specific heat capacity of ice times the mass of ice times delta theta. So I'm going to move to a new page. So that's 2.09 times 10 to the 3 times 2.21 times 10 to the 5 times the temperature change, which is 20 Kelvin. So this energy, just to raise the temperature, is 9.24 times 10 to the 9 joules, okay? So this is already larger than the available energy of 5.6 times 10 to the 8 joules, so it won't melt, okay? So that's the conclusion already. But let's see how much more energy we will need to actually melt the ice. So to melt ice at 0 degrees Celsius, and specifically, okay, and specifically 0.01, which is 1% of the initial mass, comma, we need 0.01 times 2.21 times 10 to the 5 times, which is, by the way, the mass of the ice, right? So 1% of the ice times the latent heat, which is 3.34 times 10 to the 5 joules per kilogram. And then we have another kilogram from the mass. So we will need 7.38 times 10 to the 8 joules, which is surprisingly also larger than 5.6 times 10 to the 8 joules. Okay, so the total energy needed, to melt the ice, to melt 1% of ice, is E total, let's call it prime, 1.3 times 10 to the 9 joules. So the claim is totally false, okay? So that's the answer. We don't have enough energy to do that, so claim is wrong. Okay, there is one more question, part 2. Give 2 reasons why your analysis of the situation may be incorrect. So, first of all, the sun will not be directly overhead for 12 hours because it moves, right? And also, actually the earth moves, not the sun, but okay. And also some heat will be lost to the surroundings. So yeah, this is an erroneously wrong claim. So let's move on to question 20. The infamous Petronas Towers in Kuala Lumpur. Okay, so the photograph shows the Petronas Twin Towers in Kuala Lumpur, which are the world's tallest twin buildings. Okay, I didn't know that actually. Okay. Each tower is supported by 16 cylindrical concrete columns. Calculate the stress at the base of each cylindrical concrete column. And they give you the mass of the tower, of each tower, and the diameter of each column. So we will use stress is force per cross-sectional area. The force here is just due to the weight. M times G over pi r squared. So 3 times 10 to the 8 times 9.81 over pi times 1.2 squared, which is the diameter of each column. Okay, and we need to divide the whole thing by 16, right? Because the mass is distributed over the 16 columns. Let me think. Yeah, that sounds right. So if we do that, and this is in pascals, by the way, and if we do that, we find 4.07 times 10 to the 7 pascals, or about 4.1 times 10 to the 7 pascals. Okay, that's large. Okay, B. Tall buildings sway in the wind. The design of the Petronas Towers permits safe movement of the towers. The towers were designed to permit a maximum horizontal displacement of 0.9 meters at the top of the towers. The natural frequency of each tower is 0.17 hertz. Calculate the maximum velocity at the top of one of the towers when the tower is oscillating at its natural frequency. Okay, so pretty much V max, when something is oscillating, is equal, the maximum possible speed is omega times the displacement. In this case, we call it delta x. I'm referring to the 0.9 meters they state. And omega is 2 pi times the frequency times delta x. So 2 pi times 0.17 times 0.9 yields 0.96 meters per second. That's the answer. Okay, part two. The twin towers were linked together to improve the response of the building to strong winds. The graph below shows how the maximum displacement x varies with the frequency f for a single tower and for two linked towers. Okay. Explain the behavior of a single tower compared with the behavior of the linked towers. So, I mean, we can immediately see that the amplitude is larger for the single tower than for the linked towers. And also, this is a resonance, right? And the resonance occurs at a lower frequency for the linked towers. So these are kind of things we can write. So for both towers, I mean both the single and the linked, okay, there is a resonance. There is a resonance, okay, which occurs when they oscillate at their natural frequency. Okay, the maximum amplitude for a single tower is larger than A for the linked ones, the linked towers. Okay, And resonance occurs at a lower f frequency for the linked towers. Is there anything else we can write? So there is more damping, I guess. This is why the height of the resonance is lower for the link tower. So there is more damping for the linked towers than the single tower. And then damping reduces the resonance pretty much. Okay. 21. All objects with a temperature above absolute zero emit a spectrum of electromagnetic radiation. State what is meant by absolute zero. It's the temperature at which molecules or atoms have a kinetic energy of zero. Okay, they stop moving. B. The graph shows how the intensity of radiation emitted by the Earth varied with wavelength in 2020. Explain the differences between this graph and a graph representing the emission of radiation by the Earth in 2050. Assume that the average global temperature increases over time. So if this happens, I guess we will have a new graph. Let's use red, which will have a higher peak, which occurs at a lower wavelength. Okay, so we can write down a few things about this. So the intensity of radiation is proportional to T to the fourth. That's why the red curve is has a higher peak. So higher peak for 2050. The 2050 graph shifts to the left. Okay. Lambda max occurs at the lower lambda. Okay. And lambda max can be found using Wien's law. Okay. At the end of the 19th century, Wien, I have a typo here. So Wien is written like IEN. Okay, Wien's law. All right. At the end of the 19th century, Wien investigated the radiation emitted by hot objects and formulated a law. The table shows data for some stars. Okay, there are 3 stars there. We have the lambda max and their temperature. Deduce whether Wien's law is confirmed by these data. So first of all, let's find Wien's law. It's given in the back of the paper somewhere. Let's find it. Not here. Not here. Not here. Sorry. Here. So lambda max T is equal to 2.898 times 10 to the negative 3. So let's go back. Where were we here? So lambda max times T is 2.898 times 10 to the negative 3 meters times kelvins. Okay, and let's go find lambda times T for these stars. So for Bellatrix, we have 132 times 10 to the negative 9 times 21,500. This yields 2.838 times 10 to the negative 3 meters Kelvin. Okay, that looks good to me. Okay, now for Rigel, let me know in the comments. 2.45 times 10 to the negative 9 times 11,600 Kelvin yields 2.842 times 10 to the negative 3 meters Kelvin. And then for Sirius, we have 287 times 10 to the negative 9 times 9,910 yields 2.844 times 10 to the negative 3 meters Kelvin. So Wien's law holds for these guys, okay? I mean, it's not exactly the same, but okay, hey, this is an experiment. So, and it was done in the 19th century, okay? So this was what, in the 1800s, about 200 years ago, guys. So give this guy a break. So let's move on to part D. Okay, the Hertzsprung Russell diagram below, okay, shows part of the main sequence of stars. The star Sirius A is marked on the diagram. On a website, it states that the radius of Sirius A is twice the radius of the Sun. Deduce whether the statement is correct, and they give you the radius of the Sun and the surface temperature of the Sun in Kelvin. Okay, the first step is to find the luminosity of the Sun. Okay, and you will see why. So, the luminosity of the Sun is given by Stefan Boltzmann's law, sigma times the area times t to the fourth. So 5.67 times 10 to the negative 8 times 4 pi. So this is sigma. Okay, times 4 pi, and then 6.96 times 10 to the 8 squared. So now this is 4 pi r squared, which is the area of the Sun, okay? And then we still have to multiply with the temperature to the fourth. 5,800 to the fourth. And if we carry the calculation, we will find 3.91 times 10 to the 26 watts. Okay, now it is stated that the luminosity of Sirius is 30 times that of the Sun. Okay, so that's 1.17 times 10 to the 28 watts. Okay, so if we go to the plot they give us, we see that the temperature, the surface temperature of Sirius is 10,000 Kelvin, okay? So, and the way to read this, by the way, another thing I wanted you to know about this graph is that if this is 10, this is 30, because if this is 10, then this is 20, this is 30, and then the next line is 40, 50, 60, 70, 80, 90, 100, okay? And then it goes like that. That's 100, then the next line, let me see, the next line is this one, 200, 300, 400, 500, because it's a log scale. Okay, so they tell us that it's 30 times larger. Actually, they don't tell us, I'm sorry. I think I confused you a little bit. The only thing they tell us is that the claim is that Sirius A has a radius that is twice the radius of the Sun. So we use the diagram actually to find the luminosity of Sirius, which is 30 times the luminosity of the Sun, because they give us this information in terms of the luminosity of the Sun. That's why we found the luminosity of the Sun first, okay? And now we found the luminosity of Sirius, and we know the temperature from the diagram, okay? I'm sorry if I confused you. So now we can also use Stefan Boltzmann's law again. So sigma times pi, and then r of Sirius squared times times t to the fourth will be 1.17 times 10 to the 28 watts. So we have that 5.67 times 10 to the negative 8 times 4 pi times r of Sirius squared times 10,000 to the fourth is 1.17 times 10 to the 28, okay? So the radius of Sirius squared is 1.64 times 10 to the 8 meters. So the radius of Sirius is 1.28. This is 18, by the way, I'm sorry. So 1.28 times 10 to the 9 meters. And then if we divide 1.28 times 10 to the 9 for Sirius with 6.96 times 10 to the 8, which is the radius of the sun, we find 1.84, which is about equal to 2. So yes, Sirius has about twice the radius of the sun. Right, and this was a really long paper. Again, this was paper 2.
Could you try again?
Okay, this was a long paper. It was paper 2 from 2025. When was it? I think it was June, right? Let me see. Yes, June 2025, paper 2. It was requested to me by one of you guys. This is the first time this happened. It really made my day to notice that people are noticing my work and following my work. So thank you again for emailing and the kind words. And okay, in the email, there was a request that I also make the papers 2 and 3 from 2025. So far from the UK Edexcel curriculum, I solved paper 2 from 2024 and paper 1 from 2025, and now paper 2 from 2025. I will try to populate this channel with more solutions and walkthroughs and explanations and stuff like that. Thank you for those of you who are following. Please like and subscribe, and see you in the next video.